created by MindSticks Foundation Trust.
Hello, students, and welcome to today's Explainer. We have a lot of fascinating science to cover today. First, we will look at how electricity is actually generated. Second, we'll explore the role of turbines. Third, we will dive into thermal power stations, followed by nuclear power stations. And finally, we will discuss their environmental impacts.
Section 1. How electricity is generated.
Before we can understand how massive power plants work, we must start with a basic physics principle discovered way back in the 1830s. It's called electromagnetic induction, and it was discovered by the brilliant Michael Faraday. The rule is surprisingly simple, but absolutely powerful. Whenever the magnetic field around a conductor changes, a potential difference is generated across it. So what's the big takeaway here? The absolute key to creating electricity is simply changing a magnetic field.
So, how do we achieve this in practice? Well, we can change this magnetic field in two distinct ways. Either the conductor itself moves, or a rotating magnet spins inside a stationary coil. As that magnet rotates, the magnetic lines of flux constantly shift around the coil. This changing field generates an induced electromotive force, which effectively gives us an electric current. This simple, elegant setup is the true basis for almost every electric generator in the world. Section 2. The role of turbines and how we rotate that magnet. Now, a small spinning magnet is perfectly fine for a science experiment in a lab, but to physically rotate the massive, incredibly heavy magnets used in commercial power plants, we need some serious help. We use a mechanical device called a turbine. A turbine features special blades arranged around a central wheel and shaft. When a high-velocity flow of liquid or gas, like highly pressurized steam, is strongly directed at these blades, the kinetic energy of the steam forcefully pushes them. This causes the entire wheel and shaft to spin very rapidly. And this spinning shaft, it's directly connected to our electric generator.
This brings us to a fundamental four-step sequence that applies to almost every commercial power plant on Earth. Step 1, we need a proper energy source to run the turbine. Step 2, that energy physically drives the turbine itself. Step 3, the rotating turbine drives the connected generator. And finally, Step 4, the generator produces the electrical energy we use in our homes. Let us apply this strong foundation to our first major method.
Section 3. Thermal energy power stations, where we get energy from coal.
Let's look at how electricity is produced using a very common fuel source, which is coal. Now, you don't just magically get electricity directly from a solid lump of coal. We have to trace a logical chain of energy transformation. We start with the chemical energy securely trapped inside the coal. By burning it, we convert that chemical energy into immense thermal energy, or heat. This intense heat boils water to create high-pressure steam. The steam then forcefully hits the turbine blades, transferring its kinetic energy. Finally, the spinning turbine turns the generator, converting mechanical kinetic energy into electrical energy.
In a working plant, fuel and air enter the boiler for combustion. The intense thermal energy boils the water, sending highly pressurized steam to spin our turbine. The turbine turns the generator, and boom, electricity is produced. But what happens to the steam after that? It travels into a condenser, where water from a huge cooling tower takes the heat away. This process condenses the steam back into water so it can be pumped right back into the boiler and reused in a cycle. The excess heat absorbed by the cooling water is safely released into the atmosphere as water vapor. To truly grasp the enormous scale of this, let us look at some massive facilities operating across India today. Vindhyanagar in Madhya Pradesh has a colossal capacity of 4,760 megawatts. To put that into perspective, just one of these mega plants can power millions of homes simultaneously. Other locations like Mundra, Tamnar, and Chandrapur also generate thousands of megawatts. These are gigantic, highly engineered facilities powering our modern lives using the exact steam turbine principles we just discussed.
Section 4. Nuclear energy power stations. Now consider this. What if we could boil all that water without burning fossil fuels, like coal? We absolutely can, using atomic reactions. But how does nuclear fission actually take place inside a reactor? Let's zoom in and look at the unseen chemistry happening at the microscopic level.
We start by bombarding an atom of uranium-235 with a single neutron. The atom absorbs this neutron and momentarily becomes its heavier, highly unstable isotope, uranium-236. Because of this extreme instability, the atom violently splits apart, forming atoms of barium and krypton. This split releases 3 more free neutrons, and importantly, it releases 200 mega-electron volts of energy. To picture that, it is millions of times more energy than you get from burning a single molecule of coal. It is a truly staggering amount of heat from just one single atom.
And you know what? The process does not stop there. Those 3 newly released neutrons fly off and hit 3 more uranium atoms. Those atoms split, releasing 9 more neutrons, and so on and so on. This multiplies rapidly, creating a controlled chain reaction. In a nuclear power plant, our scientists perfectly control this reaction to continuously release immense, steady thermal energy, which we then use to boil our water.
When you compare a nuclear plant to the thermal plant we saw earlier, the back end is strikingly similar. We still completely rely on the steam turbine, the generator, the condenser, and the cooling tower. The fundamental difference is entirely on the front end. The coal boiler has simply been replaced by the thick nuclear reactor and its control pods. The reactor provides the intense heat required to generate steam, doing so without burning even a single gram of carbon-based fuel.
So if we summarize the energy flow for nuclear power, it perfectly mirrors the thermal plant once the water turns to steam. We start with pure nuclear energy, convert it to thermal energy inside the reactor, create kinetic energy in the pressurized steam, transfer that to kinetic energy in the spinning turbine, and finally, generate our electrical energy. The mechanical process is virtually identical.
Section 5. Environmental impacts and the real-world costs.
While these engineering marvels provide us with vital electricity, they come with very real consequences. Burning coal results in significant and harmful air pollution, continuously emitting gases like carbon dioxide, sulfur oxide, and nitrogen oxide. Furthermore, dangerous solid soot particles are released into the environment, which can cause severe respiratory problems for people living nearby. Aside from the heavy pollution, the Earth's natural reserves of coal are extremely limited. It simply isn't a sustainable long-term fuel supply for humanity.
Nuclear power, on the other hand, does not pollute the air with soot or carbon dioxide. However, it presents its own grave set of challenges. The products left over after nuclear fission are highly radioactive. Disposing of this nuclear waste safely is an extremely challenging and dangerous task for our modern scientists. Additionally, an accident in a nuclear power plant carries the severe risk of releasing devastating radiation into the surrounding environment, which can be absolutely fatal. When we weigh these two options side by side, we face a very difficult reality. With thermal power, we face toxic air pollution and rapidly depleting fossil fuels. With nuclear power, we carry the heavy burden of dangerous radioactive waste and the looming risk of accidents. Understanding these harsh realities makes it very clear that neither of these current methods is perfectly green, nor are they without severe long-term consequences for our planet. So, based on the fundamental similarities in how these plants mechanically operate and the striking differences in their environmental hazards, I want to conclude by challenging you with this final thought. What forms of truly green energy must we actively look toward next? To power our modern civilization safely and sustainably, we must begin thinking far beyond coal and uranium. Thank you for joining today's Explainer, students. Keep asking good questions and keep exploring the science around you.